Welcome to lesson number 2. The goal of the next few videos will be to make use of an edge detection algorithm, the canny edge detection technique. The goal of edge detection is to identify the boundaries of objects within images. In essence, we'll be using edge detection to try and find regions in an image where there is a sharp change in intensity, a sharp change in color. Before diving into this, it's important to recognize that an image can be read as a matrix, an array of pixels. A pixel contains the light intensity at some location in the image. Each pixel's intensity denoted by a numeric value that ranges from 0 to 255. An intensity value of 0 indicates no intensity if something is completely black, whereas 255 represents maximum intensity, something being completely white. That being said, gradient is the change in brightness over a series of pixels. A strong gradient indicates a steep change, whereas a small gradient represents a shallow change. On the right-hand side, you're looking at the gradient of the soccer ball. The outline of white pixels corresponds to the discontinuity in brightness at the points, the strength in gradient. This helps us identify edges in our image, since an edge is defined by the difference in intensity values in adjacent pixels. And wherever there's a sharp change in intensity, a rapid change in brightness, wherever there's a strong gradient, there is a corresponding bright pixel in the gradient image. By tracing out all of these pixels, we obtain the edges. We're going to use this intuition to detect the edges in our road image. This is a multi-step process. Step 1 being to convert our image to grayscale. Why convert it to grayscale? Well, as we discussed earlier, images are made up of pixels. A 3-channel color image would have red, green, and blue channels. Each pixel a combination of 3 intensity values, whereas a grayscale image only has 1 channel, each pixel with only 1 intensity value, ranging from 0 to 255. The point being, by using a grayscale image, processing a single channel is faster than processing a 3-channel color image and less computational intensive. Let's start implementing this inside of Atom. We've already loaded and read our image into an array. Now what we'll do is import numpy as the alias np. We're going to work with a copy of this array by setting lane image is equal to numpy.copy image, thus copying our array into a new variable. It's imperative that you actually make a copy of this array instead of just setting lane image is equal to image. If we do this, any changes we make to lane image will also be reflected in the original mutable array. Always ensure that you make a copy whenever working with arrays, instead of just setting them equal directly. So what we'll do now is we'll create a grayscale from the color image. We'll do that by setting variable gray is equal to cv2, and from our OpenCV library, we'll call the function cvtColor, which converts an image from one color space to another. We'll be converting lane image, and in the second argument, for an RGB to grayscale conversion, we can use the flag cv2.color_RGB to gray. Very intuitive. And now, instead of showing the color image, we'll show the grayscale image. If we go to our terminal, python lanes.py, everything works out accordingly. This was step number 1. Step number 2 of edge detection will be to next apply a Gaussian blur on this image. Let's talk about that in the next video.